In this video, we'll continue our discussion of topics from Methods Chapter 5 on curve fitting and interpolation. We've already talked about methods for interpolation that involve finding a function that exactly matches a set of data, the Newton and Lagrange interpolating polynomials. An alternative method is called spline interpolation, where the Newton and Lagrange interpolating polynomials use all of the data in a set to calculate a single polynomial that fits all of these points. This is not possible for large data sets. And in fact, for most applications, only the interpolating curve and its first few derivatives need to be continuous. If we have 20 data points, for example, we probably don't want to interpolate with a 19th order polynomial. Instead, we use spline interpolation. Spline interpolation uses different polynomials between each pair of successive data points, but it can be done to ensure a smooth curve by matching derivatives at what are called the knots, where the knots are the data points. The knots are also the points at which we switch from using one polynomial to another polynomial. Consider this set of 11 data points connected by 10 spline segments using either linear or cubic equations. In general, if we have n plus 1 data points, they must be connected by n spline segments, which are each polynomials. For linear splines, each of the n segments is defined by a line that connects two successive points. And there will be a different line connecting the first two data points between x1 and x2, as you can see here, than the line that connects the next two data points between x2 and x3. In this case, the coefficients a and b represent the slope and the intercept of each of these segments and can be obtained from the point-slope formula for each line segment. A quadratic spline also connects n plus 1 data points using n segments, where each segment is a quadratic equation. And we would use a different quadratic for the region between the first and second points than we use between the second and third points, and so on, just like we do for the linear spline. Only now we have 3 sets of coefficients. Because each of the spline segments is a quadratic, we need a coefficient for the x squared term, a coefficient for the x term, and a coefficient for the constant term. So this requires that we find 3 n unknowns if we have n spline segments connecting n plus 1 data points. Therefore, we need 3n equations that will give us these 3n unknowns. We can obtain 2n equations by requiring that each spline segment match the data at the endpoints of the segment. So spline segment 1 has to be equal to y1 at x1, and it also has to be equal to y2 at x2, and so on, all the way through the remaining spline segments. This gives us 2n equations. Then we can make the curve smooth by matching the first derivatives at each of the interior points. This provides us with n minus 1 more equations. That is, we set the derivative of spline segment 1 equal to the derivative of spline segment 2 at the knot, x2, that connects those two spline segments. And that way the curve will be smooth. But this only provides us with n minus 1 additional equations. So we still need one additional equation. That additional equation is obtained typically by setting the second derivative of the very first spline segment equal to 0 at the left end, which means that the x squared term in the first spline segment is 0, or the first spline segment is actually just a straight line connecting the first 2 points. And the slope of that line is the initial slope of the second spline segment. These 3n equations can all be solved simultaneously for all the coefficients of each spline segment in the vectors a, b, and c that would define the cubic equations that are used for the spline segments. Since all of the x and y are known at each of the n plus 1 data points, we can make these 3n linear equations. If we have 4 data points with 3 quadratic spline segments, then there are 9 linear equations that we need to solve for 9 unknowns. And those linear equations can be formulated into a matrix that looks like this. The first 6 equations, indicated in red here, are found by enforcing the constraint that the endpoints of each of the splines has to match the data at the knots. The first spline segment has to match y1 at x1, and the first spline segment also has to match y2 at x2. Then the second spline segment, containing coefficients a2, b2, and c2, has to match y2 at x2, and it also has to match y3 at x3. The two equations represented here in blue enforce the constraint that the derivatives have to match at the interior knots. That is, the derivative of the first and second spline segments should be equal at x2, and the derivative of the second and third spline segments should be equal at x3. And then the last constraint here is simply that a1 equals 0. That gives us the 9 equations that we need for the 9 unknowns, which are the coefficients of the quadratic equations for the 3 spline segments connecting the 4 data points. While linear and quadratic splines are useful for illustrating how splines are generated, they're not typically used for interpolation. Often, cubic splines are used instead, and we'll introduce cubic splines in the next video segment.